Okay, so the very last section of chapter 1 breaks away from equations and starts a conversation on inequalities, specifically linear inequalities, compound, and absolute value inequalities. So a lot of variety in this section. Um, Later on down the road, we will expand on our work with inequalities that we're going to do right here, right now, by solving those that involve polynomials and rational equations. Taranjot, as I mentioned at the start of class, I'll be sending out more information as we get closer. All right, so right now I'd just like to focus on 1.7. If you want, you can stop in during my office hours today. I'll be happy to answer those questions for you, but I don't want to get off track here. So in this section, we're going to focus on the linear, compound, and absolute value. We'll probably have enough time for the linear and the compound. We'll have to take care of the absolute value at a different time. But let's start with a linear inequality. Okay, this is going to be a linear inequality involving just one type of variable. And these things are expressions that are separated by one of these four symbols, which are our famous inequality symbols. And the way we solve these sorts of linear inequalities is much like we would an ordinary equation, but there's an important detail that I'll discuss in just a second in this context. Another type of inequality is known as a compound linear inequality in one variable. And the deal with these is that they'll include two or more linear inequalities. And there are really two types of compound inequalities. There's something known as the AND compound inequality. And with an AND compound inequality, you usually have some sort of algebraic expression. I'll write it as ax plus b, set between two different numbers, which I'm going to put a generic c on the left and a generic d on the right. And separating the expression from these two numbers will be a couple of less than symbols, sometimes less than or equal to, or a combination of less than and less than or equal to. The other type of compound inequality is the OR compound inequality. And the OR compound inequality has two linear inequalities that are separated by the word OR. So they're not really meshed together like the expression that we're seeing for the AND compound inequality. So to write this out in a generic way, I'm going to say ax plus b is greater than or equal to c. And we'll usually include the word or. And I'll say dx plus e. And I'll change the symbol to maybe less than or equal to f. But the major difference is that we have separation by the word or, and the inequality symbols can be any mixture, to be honest with you. But how we solve the and versus the or is starkly different. With the and compound inequality, our job is to get x by itself in the middle of the inequality symbols. With the OR compound inequality, we solve for x in each of these inequalities separately. And so what you'll see me typically do is draw a little boundary line, in which case I solve the first inequality on the left of it, the second inequality on the right of it, and at the very end, I don't join them together like you're seeing with the AND compound inequality. So everything just stays separated even through the very end. So before we get to solving a couple of inequalities, a couple of important things. The first is something I was mentioning a minute ago. When you solve linear inequalities, you want to treat it like you're solving a regular equation. However, whenever you multiply or divide both sides of an inequality by a negative number, does anybody remember what you have to do with the inequality symbol? Yeah, you have to flip it. A lot of people like to say you switch it. All right, but flip works just as well. I'll sometimes say reverse, but either way, the inequality symbol is changing direction, okay, when you multiply or divide by a negative number. Okay, and it's only those two operations. If you have to add or subtract, you don't have to worry about flipping the symbol. Another thing regards the instructions. Some of the instructions might say, provide a graph of the solutions. Right? And what a graph of the solutions is a number line with the answers for x being shaded. So as you might recall, if you've worked with inequalities before, instead of getting a single solid answer for x, we usually get very many answers for x, infinitely many. And so it's not really possible to write each individual value for x out separately. There's just too many of them. So we instead give like a visual representation, and we also use something called interval notation. All right, so I'm going to cover those details when we solve these inequalities. Let's start with part A. We have 1 minus 2x is less than or equal to x minus 5. So just one inequality symbol involved with this one, making it a linear inequality and not one of those compound inequalities. We want to treat the inequality symbol as if it were an equal sign. So what I would start things off with is perhaps subtracting x from each side, which doesn't require flipping the symbol. That's to cancel the x that's on the right-hand side. On the left, we would get 1 minus 3x less than or equal to negative 5. From there, I would subtract 1 from each side to get negative 3x on the left is less than or equal to negative 6. I would then move on to divide each side by negative 3. Now, notice that we divided by a negative number. That means we're going to have to flip this symbol. Okay, so it's no longer a less than or equal to, it becomes a greater than or equal to. On the left, things simplify to x, and on the right, things simplify to 2. And once you have x isolated, you've solved the inequality, and the version of the answer that you get is what I like to call the inequality version of the solution. But they also want us to provide a graph and write things in interval notation. Okay, before I do that, do you have any questions about the algebra? So I usually do the graph first because it's very easy to jump to interval notation from the graph. So I'm going to draw a number line, and there's one value that we're comparing x to, and that's the number 2, which I'll put a tick mark on it right in the center. This answer, x is greater than or equal to 2, wants us to focus on numbers that are larger than 2, but we could also include 2 itself. So if this is our number line, where do those values of x fall? Would they be to the left of 2 or to the right of 2? They'd be to the right of 2. And actually all these numbers that are to the right of 2 would satisfy our inequality x is greater than or equal to 2. So what I've done is I've shaded this part of the number line, and any number that's in the shaded region actually serves as a solution to our inequality. And this shading actually continues forever to the right. And to indicate that, we'll use the infinity symbol. And I like to say that the shading is going from 2 all the way down to infinity, even though infinity is not a stopping point. Okay. Now to indicate that we can include the value of 2, in the past you may have used a closed circle, but in this class we're going to use a bracket. Now if we are not supposed to include 2, we would use a parenthesis. So we are including it, and that's indicated by the bar. And so what I'm going to do is I'm going to put a bracket on top of the tick mark and pointing to the right. So pointing in the direction of the shading. And this is what would be a legitimate graph of the solutions. For interval notation, here's what we do. We look at the smallest and largest number involved in the shaded part of the number line. The smallest number involved is 2, and even though it's not a number, I'll consider the largest number infinity. Let's write 2 down with a comma directly after it. You always write the smaller of the two numbers first, comma, and then you write the larger of the two numbers, which is infinity. And with interval notation, you're going to use brackets and parentheses as well. And which one you use is dependent upon what you're seeing on your number line. There's a bracket on the 2, which is why I'm going to put a bracket right in front of our 2. And by default, there's always a parenthesis on infinities. So whether it's negative infinity or positive infinity. So for that reason, I'll put a parenthesis to close off this notation, which this notation that I have right here is what we refer to as interval notation. And does that look familiar to anybody? All right, cool. Well, let's see if we can knock out one more. This would be an example of the and compound inequality, just by way of how it's designed. And as I mentioned up there, the name of the game here is to get x by itself in the middle. So you are able to do that. And to start things out, we're going to add 3 to the middle part of this. And the way the and inequalities work is that whatever you do to the middle part to try and get x by itself, you have to do to the outside parts as well. So if I'm going to add 3 to cancel out this negative 3 in the middle, I have to add 3 to the left and right numbers as well. That gives us 2 is less than or equal to 2x is less than 8. Next thing we want to get rid of is this 2 that's in front of x, and we can do that by dividing by 2. Now bear in mind, whatever you do to the middle, you have to do to the outsides as well. And so we'll have 1 is less than or equal to x is less than 4. And now that we have x in the middle all by itself, we've actually solved this compound inequality. Let's draft up a number line, because we still need a graph and the interval notation. And this time we're comparing x to 2 numbers, 1 and 4. So I'll put a tick mark for 1 and a tick mark for 4. Now I like the and compound inequalities with regard to graphing, because how we see x in this version of the solution is how we'll shade on the number line. With this inequality version of the solution, x is between 1 and 4. Okay, so that means that we want to include x values that are between 1 and 4 on the number line. So what happens is you shade in between these two numbers. We still need to decide on parentheses and brackets. Would anybody like to help me with what symbol we should put on the tick mark for 1?
Would you just put a parentheses on that one? Because it's the smaller of the two?
Well, that's a good guess. It is going to be a bracket though, because how we're comparing it to x is with a bracket. Or I'm sorry, there's a bar underneath the inequality symbol.
Oh, I got you.
So you would use a bracket. But notice there's no bar underneath the inequality symbol associated with 4. So this is where you would use a parenthesis. That make sense?
Yep.
All right. So with the interval notation, smaller of the two numbers is a 1, the larger is a 4. And based on the number line, we would put a bracket on the 1 and a parenthesis on the 4. And there we have both our graph of the solutions as well as the interval notation. Okay. So that's about as far as we can get for now in section 1.7. Do you guys have any questions about the solutions to both of these? We didn't flip the inequality symbol because we didn't divide by a negative number. It's only if we divide or multiply by a negative number. Anything else is, no change. Last two examples of section 1.7 on the screen. I'll recap this, and if you have any questions along the way, feel free to let me know. So we ended off at this part of the section 1.7 notes last week, and the last part deals with things that are called absolute value inequalities, and as you might imagine, they are inequalities that have absolute value symbols somewhere in them. And I presented a couple of rules that you could use which will help you eliminate the absolute value symbol, which is key. It allows us to solve for x, which is typically on the inside of the symbols. And there are some prep steps that you might need to take before you apply the rules. For instance, you do need the absolute value isolated on one side of the inequality. And if it's on the left-hand side and the symbol involved in the inequality is a less than, which I like to rephrase it as less than, then you're allowed to remove the absolute value symbols provided you rewrite the expression as an and compound inequality. So we squash the inside expression between the negative version of the number on the right and the positive version. All right, and then we stay consistent with the type of inequality symbol that we're using. And basically we form 3 pieces, okay, opposite numbers on opposite ends, and then the expression that was inside the absolute values in between it. But you're not done from there. Usually you have to isolate x still in the middle all by itself, and that's something we took care of last week. If your inequality symbol is a greater than, or even a greater than or equal to, which I like to phrase that as greater, then it splits up into the or compound inequality. So the first inequality of the two is basically the same inequality except the absolute value symbols are removed. And then usually this expression for u involves x, so you would continue solving from there. We write the word or in our little boundary line so we don't blend things together. And on the other side of the or, we have the same expression again, but a couple of changes take place. We reverse the inequality symbol and we change the number to its opposite. Okay, and so there were a couple of examples involving isolating the absolute value and then applying the 2 rules. And here's where I'd like to pause and ask if you guys had any questions about the solutions here, if you worked on them prior to today. So also in the video is a way of solving these things graphically. So when I present the next couple of examples, the bonus examples, I guess I'll say, we'll do an algebraic solution to the inequalities as well as a graphical solution. All right, the graphical solution, you know, you kind of have to train your eye to see the different parts that are relevant to the problem. But usually that eye gets trained really fast, you know, with just a few additional practice problems. So hope to accomplish that along the way as well. All right. So I'm going to jot down the first of the extra practice absolute value inequalities. Call this example 1. Let's do the absolute value of x plus 4 plus 3 is less than 5. Okay, so your first focus should be on isolating the absolute value, which it's not totally isolated. There is the addition of 3 right behind it. So to isolate this, we'll subtract 3 from each side. That leaves us the absolute value of x plus 4 is less than 2. Notice there's nothing in front of it, nothing behind it now on the left-hand side of the inequality symbol. And speaking of, that inequality symbol is a less than, or as I'll write, less than. So with the absolute value isolated and our understanding that this is a less than symbol, we can begin to apply the rule where it allows us to rewrite this in the form of an and compound inequality. And what I mean by that is the expression x plus 4, I'm going to write down between two numbers. The number on the left is the opposite of the 2 that's involved in our inequality. And then the number on the right will be the positive version of it. And keep in mind the inequality symbol involved is the less than symbol. So we're going to put a couple of less than symbols to separate the middle part from the opposite numbers. So far, so good? Alrighty. So what you want to do from here is isolate x. And we can do that by subtracting the 4 that's being added to it. You may recall, though, anything that we do to the middle, we have to do to the outsides as well. Negative 2 minus 4 is negative 6. We'll continue with the less than symbol, x in the middle now, and then that's less than negative 2. And since x is isolated in between the inequality symbols and everything is simplified, this would be our inequality version of the answer. But a lot of times you get asked for the graph of the solutions as well as interval notation. So let's do that. Now we're going to use our inequality version of the solution for the graph. The two numbers that we're comparing x to are negative 6 and negative 2. So let's make tick marks for each of those. And because, you know, visually speaking, it looks like x is between negative 6 and negative 2, that's a clue as to where you'll shade on this number line. And that would be none other than in between negative 6 and negative 2. Now, can anybody tell me what symbols we'll be using on these endpoints, negative 6 and negative 2? And you have two options. You could use a parenthesis or you could use a bracket. Which one would make the most sense here? Yep, parentheses. You guys got it. And the reason for that is because there's no bar underneath the inequality symbols in that version of the answer. So this would be our graph. And then for interval notation, we write down the smallest number involved in our diagram, which is negative 6. Then we write comma. And then we write the largest number involved, which is negative 2. And the symbols that we used on them with the number line are the same symbols we'll use in the interval notation. And there we have it. Now this does look a lot like an ordered pair of a point, so sometimes I'll just indicate to myself that this is interval notation, just so that I understand that, this is a section of the number line and it's not a point in the plane. All right, so I'll give us another problem and maybe have you guys work on the algebraic solution for a few minutes. Then we'll go over the solution together. Then I'll show you how you can solve these things with the graphing calculator. But the last problem for this quick recap is going to be the absolute value of x minus 2 plus 2 is greater than or equal to 3. Okay, so can I have you guys work on that for a few minutes, and we'll go over the solution once time's up. All right, so I'll show you what I did. You can compare your work against mine. The absolute value, again, is not isolated, so we'll start things out by doing that. Get the absolute value of x minus 2 is greater than or equal to 1. Okay, nothing in front, nothing behind, therefore it's fully absolute or fully isolated. But let's take note of the inequality symbol involved this time. It's a greater than or equal to. So this is going to split into the or compound inequality. So let's take x minus 2. We will set it greater than or equal to 1. Let's write the word or. We'll take x minus 2 again. Keep in mind there are a couple of changes that we make to get the rest of this inequality. I'm going to draw a little diagram here. We're going to flip and negate. So what I mean by that is we're going to flip the inequality symbol, less than or equal to, and we're going to change the 1 to a negative 1. Okay, really key detail right there that is easily missed. So just be careful, take your time, make sure you got that set up correct. We will separate all of our work, which really isn't all that much. We'll just add 2 to each side. X is greater than or equal to 3. Add 2 to each side here. X is less than or equal to 1. Oops, positive 1. All right, did you guys come up with that? Okay. Let's do a number line. Two numbers we're comparing x to are 1 and 3. So we'll put a tick mark for each of those. Hopefully that doesn't tick anybody off. And let's start with this first inequality. This is asking us for x values that are greater than or equal to 3. And those x values would fall to the right of 3. And they go from 3 all the way down to positive infinity. And does it make sense why we would use a bracket on the 3? All right. So the next inequality asks us for x values that are less than or equal to 1. And all those x values would fall to the left of 1. And they would go all the way down to negative infinity. And we would use a bracket on the 1 as well. All right. The reason for these brackets is because the inequality symbols involve the bar this time. Now, how do we write out the interval notation for the solution? Well, there are going to be two intervals here. Okay, two sections on the number line. Let's start with the first section. This starts from negative infinity. Okay, so that's the smallest number involved, and then it ends at 1. We'll bracket the 1 just based on our number line, and by default, parentheses on any infinity symbols. And then the second section starts at 3. That's the smallest number. Then the largest number involved is infinity. Bracket on the 3, parentheses on the infinity. And then we'll link these two sections of the number line together with what's called a union symbol. All right, and that's not like blending the two sets together. It's just saying, hey, you can have x values from, this section of the number line, but you can also, choose values of x from this section. So it's just kind of like grouping them together to form a cohesive solution. And that would be the interval notation. Do you guys have any questions about any of my work? Okay. Well, I'd like to go ahead and do graphing calculator solutions to these. Let me jot down the first inequality again. Absolute value of x plus 4 plus 3 is less than 5. So to solve this with the graphing calculator, you want to use either the intersect feature or zero feature approach, even though we're using an inequality symbol instead of an equal sign. That inequality symbol, though, is key to what we do after we have the graphs going. Now notice no side of this inequality is 0, so we might consider using the intersect feature. And remember, the intersect feature requires two equations in the y equals menu. The first equation, y1, I'll define as the left-hand side. And the second equation, y2, is what I'll define as the right-hand side of this. So let's go to our graphing calculators and get these entered in. Y equals. And to get the absolute value symbols, you press math, you arrow over to the number column, and it's option 1, ABS. So if it hurts to laugh tomorrow, you can blame this class for it because we're working to abs. All right, so I have absolute value symbols on my screen. Some of you might have the 3 letters ABS with a half set of parentheses. That's okay. Regardless of what you have, let's type in x plus 4. Now, if you are seeing ABS with a half set of parentheses, now would be a good time to close off those parentheses. For those of you that are seeing what I'm seeing, we'll hit the right arrow key to get out of the absolute value symbols and then type in plus 3. And we'll scroll down to y2, type in 5. And then we'll do zoom option 6. And make sure you do that clearing your throat noise when you do that. That's really key and part of the process. Just kidding. But are you guys getting the same graphs that I'm getting? Sweet. All right. Now, let me sketch those out. Very good. Y1 did something like that. Y2. We would use the intersect feature to find the 2 points of intersection. And just to save on some time, I'll provide these ones for you. This first point of intersection is at -6, 5. The second point is at -2, 5. And you'll notice that the x-coordinates of each of these 2 points are related to our interval notation. The endpoints of the interval notation involve -6 and -2 as well. Now, if this were an equation, we would be all done. We would just look at the points of intersection and keep the x-coordinates. But it's an inequality this time. And so there's a little bit more that we have to do with our diagram. And the first part of that little bit more is to make tick marks on the x-axis underneath each of these points. Label them with the x-coordinates, so -6 and -2. And basically what this does is it turns the x-axis into a number line, which it technically already is, but it breaks it up as well, okay, into 3 different sections, much like our graph of the number line did when we put -6 and -2 on it. Now I'm going to rewrite this inequality that I wrote out in the beginning. Keep in mind that the left-hand side is y1 and the right-hand side is y2, so that inequality can be rewritten as y1 is less than y2. Okay, because we defined y1 and y2 as the left-hand side and the right-hand side. Now this is important to keep in mind because from a graphical standpoint, the less than symbol takes on an important meaning. When we're trying to solve y1 is less than y2, geometrically we're looking for the parts of y1 that are under or below any parts of y2. So take a look at our diagram. Is there any part of the graph of y1 that falls underneath the graph of y2? And if so, how many parts do that? So keep in mind, yep, there's just one part. And the answer definitely is a resounding yes to my question. So I want us to focus on this part right here. Okay. That part is trapped between the 2 points of intersection. And so if we look at the first point of intersection, the one that's on the left, as soon as you go a little bit to the right of this point of intersection, the graph of y1 dips underneath the graph of y2. And it stays underneath the graph of y2 until we get to our second point of intersection, in which case the graph of y1 continues on hovering above the graph of y2. So there is a section of the graph of y1 that is under the graph of y2, and it would be this one right here. And once you've found the part or parts of the graph that correspond to your inequality symbol, you steal the x values from the x-axis that match up with the piece. And the x values that match up with this piece of the graph of y1 are the x values between -6 and -2. And that would be a picture of our answers, which confirms what we got from our algebra solution. All you would have to do from here is just write out the interval notation. The smallest number on that part of the x-axis is -6. The largest is -2. And keep in mind, we have a less than symbol with no bar underneath it, so we would use parentheses around each of those two numbers. Does that make sense? Okay. Well, let's do this with our second example. I'll at least start you out on it. Again, you want to consider using the intersect feature. No side of this inequality is 0. I would define your left-hand side as y1. Your right-hand side is y2. And I'll help you reinterpret this inequality using y1 and y2. We could rewrite that absolute value inequality as y1 is greater than or equal to y2. Okay, so you would get the two graphs of y1 and y2 going. You'd also want to find their points of intersection. But remember, that's not all that you have to do. You have to determine which parts of y1 are relevant to the problem. Now, less than tells us to look for parts that are under the graph of y2. The greater than symbol would tell us to look for the parts of y1 that are above the graph of y2. Okay? So let me go ahead and give you guys some time to graph these two equations out, find the points of intersection, and determine if there are any parts of the graph of y1 that are above the graph of y2. All right, I'll check in with you in a few minutes. All right, so let me do a rough sketch of graphs of y1 and y2. You guys getting something like that? Awesome. Can anybody provide the 2 points of intersection if they found them? 1, 3, yep. And then 3, 3. Very good. Correct. It's from SpongeBob. So if this were an equation, we'd identify the x-coordinates of each point and be done. But again, inequalities, so there's a little bit more that we have to add on to this graph or this diagram. And we'll start with tick marks corresponding to each point on the x-axis, 1 and 3. Okay, notice that 1 and 3 were involved in our algebra solution or interval notation. And we're looking for parts of the graph of y1 that are above the graph of y2. Let's look at this first point of intersection, 1, 3. To the left of this point, we're seeing green above blue, and that would be a piece of the graph of y1 that's above the graph of y2. Let me go ahead and highlight that for you. Okay, anything to the left of 1 is going to have a piece of the graph of y1 that sits higher than the graph of y2. So that section of the graph will help us identify some of our solutions for x. Namely, the x values that correspond to this piece are those that are between negative infinity and 1 on the x-axis. Okay, all of those correspond to this piece right here. Now if we go to the right of that point of intersection, we have y1 dipping underneath y2, and it does so until we get to our second point of intersection at 3, 3. And as we go further to the right of the second point of intersection, the graph of y1 begins to be above the graph of y2 again. And so this is a piece of y1 that we're interested in as well, because that's above y2, and the x values that correspond to it are those that are between 3 and positive infinity. And so we get 2 sections of the x-axis that serve as our solutions, much like we got 2 intervals for interval notation. So let's whip up intervals for each of these. The first is negative infinity, 1. There's going to be a bracket on the 1 since our inequality has a bar. And we're going to union this with bracket 3, infinity. And there we have it.